You know, when you hear string theory, you probably think about the absolute smallest things you can imagine, right? These tiny vibrating strings of energy. But what if I told you that same theory might hold the secrets to the biggest things in existence? We're talking the origin of the universe, what's really going on with black holes, and maybe, just maybe, the existence of other universes. Okay, let's get into it.
This is it. This is one of the deepest questions we could possibly ask, and today we're going to see how string theory is taking a serious crack at answering it, along with a few other cosmic puzzles that keep scientists staring at the ceiling at night.
So here's our roadmap. We're going to see how the physics of the incredibly small could give us some absolutely mind-blowing answers about the incredibly large.
Yeah, string theory started out as a way to understand particles, but oh boy, its ambitions have gotten a lot bigger. Now it's aiming for the whole cosmos, offering a potential key to unlock some of the most profound secrets out there. And really, what better place to start than at the very beginning?
The story we all know is the Big Bang, right? This massive explosion from a single, infinitely dense point. But string theory comes along and offers a different origin story, one that's maybe a little less chaotic.
See, the classic Big Bang model has this huge problem right at the start. It's called the singularity, and it's basically a point where all our known laws of physics just completely fall apart. String theory dodges this whole issue by suggesting it wasn't an explosion from a single point, but a collision.
They call it the ekpyrotic model, and the idea is pretty wild. Imagine our whole universe exists on this giant membrane, or a brain for short, kind of like a huge sheet of paper. Now picture another one of these brains, another sheet of paper, just floating parallel to ours in a higher dimension we can't see. In this theory, the Big Bang was actually the moment those two brains gently clapped together, releasing all the energy that became, well, everything.
And if that collision could happen once, why couldn't it happen again and again? This idea opens the door to something even bigger, a cyclic universe, one that has no real beginning and no real end.
So in this model, the universe is just in this endless cycle. You get a big bounce from the brain collision, which kicks off the expansion we see today. Then, over trillions of years, everything slows down, reverses, and contracts into a big crunch, which then sets up the next bounce. Our Big Bang might just be the latest breath in an infinite cosmic cycle. How cool is that?
All right, so from the beginning of time itself, let's jump to one of its most mysterious creations, black holes. These things are a huge headache for physicists because they're where our two best theories of the universe, general relativity and quantum mechanics, go to war with each other. And it all centers on a crisis about information.
Now, to get what's going on, we have to talk about something called entropy. It's a fundamental rule in physics that the total entropy, which is really just a fancy way of saying the total information in the universe, can't ever be destroyed. You know, you can scramble an egg, but you can't unscramble it. The information about the original egg is still there, just mixed up.
So here's the paradox. What happens if you throw something with information, a book, your laptop, an entire star, into a black hole? It seems to just disappear. And if that black hole eventually evaporates away, is all that information just gone forever? Poof? If it is, that breaks one of the most basic rules of quantum mechanics. It's a huge problem.
The argument over this got so heated, it was literally called the Black Hole War. But string theory came to the rescue. It suggested that the information doesn't actually get lost inside the black hole. Instead, get this, it's sort of smeared and encoded on the black hole's two-dimensional surface, the event horizon. It's like a cosmic hologram. This brilliant idea saves quantum mechanics and shows how information is never truly lost. Okay, we've talked cosmic origins, we've talked black holes. Now let's talk about what our universe is actually made of. Because it turns out, everything we see, all the stars, the planets, you and me, that's only a tiny, tiny sliver of what's really out there. The rest is a total mystery.
So astronomers were looking at galaxies, and they realized something was very wrong. They were spinning so fast, they should have just flown apart. The only thing that could be holding them together was the gravity from a whole bunch of something massive and totally invisible. They called it dark matter.
The big thing to know about dark matter is that it doesn't interact with light at all, which is why we can't see it. And while we haven't found a dark matter particle yet, string theory actually predicts a whole bunch of new, heavy particles, things with cool names like neutralinos, that could be perfect candidates for this mysterious stuff.
This leads us to our final and maybe the most mind-bending mystery of all. Why are the laws of physics in our universe so perfect? I mean, just perfect for life to exist. If you tweaked some of the basic numbers of the universe by even a tiny fraction, stars wouldn't light up,
planets wouldn't form, and we definitely wouldn't be here talking about it.
It's a question that obsessed Einstein. It really feels like our universe has been exquisitely fine-tuned. So, was that just an unbelievable stroke of luck, or is something else going on?
Well, one possible explanation is called the anthropic principle, and it basically says, well, of course the universe looks perfectly designed for us. If it wasn't, we wouldn't be here to notice. It's a bit like a fish wondering why its world is so perfectly suited for life with water.
But string theory offers a more concrete and even crazier idea. It suggests our universe isn't a one-off. It's just one bubble in a huge cosmic foam of other universes, a multiverse. And in each of those bubble universes, the laws of physics could be totally different.
How many different possibilities are we talking about? Some calculations in string theory point to the number 10 to the power of 500. That's a 1 with 500 zeros after it. I mean, that number is so gigantic, there are more possible universes than there are atoms in our entire observable universe. When you're dealing with that many chances, it's not so surprising that at least one of them, ours, would hit the cosmic jackpot.
So, from cyclic universes to holographic black holes and the multiverse, string theory just completely reshapes how we can think about our cosmos. It forces us to ask the biggest questions out there. Is our universe the only one? Was the Big Bang really the beginning? And are the rules that govern our existence set in stone, or are we just the result of a lucky roll of the cosmic dice?